Today we will be hosting Erdem Bıyık from UC Berkeley. We haven't met before in person, so this is the first time that I'm basically that I have met him, well, at least face to face. Erdem is a postdoctoral researcher at Center for Human Compatible Artificial Intelligence at University of California, Berkeley. He has received his BS from Bıyık University in 2017 and a PhD from Stanford in 2022. His research interests lie in the intersection of robotics, artificial intelligence, machine learning, and game theory. He's interested in enabling robots to actively learn from various forms of human feedback and designing robot policies to improve the efficiency of multi-agent systems, both in cooperative and competitive settings. He also worked at Google as a research intern in 2021, where he adapted his active robot learning algorithms to recommender systems. He will be joining University of Southern California as an assistant professor in 2003. And today he will be talking about learning preferences for interactive autonomy. And without further ado, I would like to leave the stage for him, and I'm looking forward to his talk. Thanks.
Thanks, Erol Hocam, for the great introduction. And I'm assuming you are seeing my slides now. Okay, great. Hello everyone. I'm Erdem Bıyık, and as Erol just said, I'm currently a postdoc at UC Berkeley. I'm working with Professors Stuart Russell and Anka Dragan in the Center for Human Compatible AI. And today I'm going to talk about learning human preferences from interaction data for developing robots and AI agents that better collaborate with humans. And most of what I'm going to talk today is from my PhD work at Stanford with Professor Dorso Sadiq. So I want to give some credit for my former institution too. So in my research, I work on human-robot interaction and multi-agent systems, such as a human and a robot collaborating on stacking a burger or building a structure together, or assistive settings such as an exoskeleton helping a person walk, or larger multi-agent systems where we have a number of autonomous cars interacting with a large number of human-driven cars. So in all these domains, robots should first learn the behavior of other agents in order to better interact with them. For example, our robots should anticipate human actions to improve efficiency in human-robot collaboration, or increase comfort and safety of an exoskeleton, or reduce congestion in a traffic network. So how can we make these robots learn the behavior of the humans or other autonomous agents that they're interacting with? Maybe machine learning is the answer. We just need to collect some large data sets and train a large model to learn these behaviors. We have seen this as a successful approach in many domains. For example, OpenAI trained GPT-3 using 45 terabytes of data, and they achieved to produce human-like texts. And more recently, there is ChatGPT. I'm sure most of you have already played with it, and it's based on a lot of data. Or there is ImageNet. It consists of 14 million images, and it led to very successful image recognition models. AlphaZero played millions of chess games on its own, and it became a superhuman chess engine. So it seems like this collecting large amounts of data idea, it just works. But what's the state in robotics? Today, the state of robot learning looks like this. This is a video from Google's ARM farm. So a few robots are working nonstop to learn hand-eye coordination. But compared to millions of chess games every day or the text data from the entire internet, this is almost nothing. And the problem gets even harder for human-robot interaction tasks because we need human models. We need to learn from humans. So in addition to the cost of the robots, we need real people to sit in front of these robots and control them or interact with them. And that's way too expensive. So in my research, I developed efficient robot algorithms that can learn from the sparse data available in an environment, and then use what they learned for their interaction with other agents. And for this, I focus on three fields. First, I study human-robot interaction, because if we want robots to effectively help or collaborate with humans, we need them to learn humans' objectives. But the agent we are trying to learn doesn't need to be a human. So I also look at multi-robot or multi-agent systems in general. And eventually, when we learn these other agents' objectives, we want this information to help our robots in various ways. For example, we want to use those models while planning for our robots. So I've done research on these three fields, and today I'll talk about only a subset of my work focused on how we learn humans' objectives. And I'm going to divide this talk into three parts. First, I'll start with learning from comparisons, where the goal is to learn humans' objectives based on their feedback. Then I'll talk about how we can learn more expressive models from a mixture of human data using multimodal rewards, where the data may come from multiple humans with different objectives. And finally, I'll move to the third section, which I call active querying. The idea here is that data collection is very expensive for robotics tasks, especially if the data is coming from humans. So we should try to collect the most useful, most informative data for our purposes. It's an active learning problem where we have two-way interaction now. So let's start with how we learn other agents' objectives. So one very common way to learn objectives is to collect some demonstrations from the agents the robot is interacting with, and then learn a policy or a reward function for them. For example, behavioral cloning is one such idea that has been around for more than 30 years now. And these learning from demonstration techniques, they work great in many settings. For example, many works, including some of ours, used learning from demonstrations to learn safe and efficient policies for autonomous cars. But these techniques are usually not sufficient for learning an optimal policy, especially like in driving too. For example, in our work shown in the middle, we had to learn multiple policies and try to optimally switch between them. So what's wrong with these methods? Why can't we just imitate the human and have a perfect driving policy? One of the reasons for this is human demonstrations, so humans themselves, are often suboptimal. To more concretely see why learning from demonstrations may fail, let's look at the problem mathematically. So we are given a set of demonstrations, which I call the set D. So each variable here, each xi here is a trajectory, right? And let's say there is a function phi that maps each trajectory to a set of features. For example, here is a robot trajectory where the goal is to reach the notebook on the desk without colliding with the obstacle. Of course, this is an easy task, but the algorithms I will talk about today are application agnostic, so you can use them for more complex tasks too. I will show simple tasks so that like we only focus on the algorithms, not the applications. So here in this task, the set of features can be, again, for example, final distance to the goal, how close the robot gets to the obstacle, its average speed, etc. And the assumption is the robot is trying to optimize an objective, and this objective, the reward function we are trying to learn, is a parameterized function of the features. So essentially what I'm trying to do is to learn these parameters W. One way of doing this, learning from demonstrations, is through an approach called Bayesian inverse reinforcement learning. So in this method, we find the posterior distribution of the parameters vector W given the demonstrations. We can then take its maximizer or the expectation as our learned reward function. Or we can even use it as a distribution if we need to model uncertainties. So how do we do this? Well, we use Bayes rule. Here, the first term is just the prior. We can take a uniform distribution for that, or we can incorporate our domain knowledge. But the important term here is the second term, because it will add the information from our demonstrations into the model. And for that, in Bayesian IRL, we first assume the demonstrations are conditionally independent. So given the reward function, the user's demonstration to the robot doesn't depend on their earlier demonstrations. And also the likelihood of demonstrations, again, we assume they come from a noisily optimal human model, the softmax rule in this case. This final expression is an unnormalized distribution that we can use as our posterior. But the problem here is that the noisily optimal assumption, it doesn't hold. So even though this human model tries to capture human suboptimality, it asserts the optimal trajectory is the most likely demonstration, because as you can see, we are assuming the likelihood of a trajectory is proportional to exponential of its reward. So the optimal trajectory must be the most likely trajectory. But for example, the trajectory that I'm showing here in the picture, it's the optimal trajectory, but it's definitely not the most likely one, because humans will not be able to teleoperate the robot to move as smooth as this. And in fact, this robot is just too difficult to control. Here you are seeing my lab mate, Andy. And Andy has a lot of experience with this robot. He's trying to teleoperate it to perform the task that I described, but he's having a hard time because this robot arm has 7 degrees of freedom. So it's really hard to teleoperate it. And also the problem is not specific to teleoperation. In fact, humans are far from being optimal decision makers. There's a work from Berkeley, from Anka's work actually, where they showed humans do not like their own driving. They think it's too aggressive. And more recently, we showed that humans are consistently making suboptimal decisions when they encounter situations that involve risk. This is from like behavioral economics. It's a known phenomenon. And if we are not able to give good demonstrations, if we are not able to like give good decisions to these like robots, then how can we even hope to learn from these demonstrations? So we need a better way of learning objectives. And our idea is to have the robot itself demonstrate a trajectory to a human. And then the human will assess how good, how successful that trajectory is. But this is also not an easy task for the humans. They often provide unreliable data. And it might not be obvious why. To make it more clear, let me ask you a seemingly unrelated question. How dark is this blue? For such a question, you may say things like a little bit, or it's not that dark, etc. But when someone says a little dark, that's very ambiguous. And in fact, we humans are not very good at making these kind of assessments or giving ratings. So when I ask a user how good a robot trajectory is, they may say things like, that's kind of good, or no, a little bad. And these kind of responses are very ambiguous for me. Instead, we are better at comparing things. So instead of asking how dark is this blue, let's say I introduce a second color and ask which blue is darker. Now, all of you will give the same response to this question. It's very reliable. And we actually, like as humans, we actually generate comparison data all the time. Like every time we make a selection in Uber or Lyft, or every time we click on a YouTube recommendation, it's a preference over other options. Similarly, our actions generate comparison data. For example, Google Maps gives us multiple navigation options, and we take one of them. Google then understands we prefer that route over the others. So we implicitly make a comparison. And our idea in this research is to have robots leverage such comparative data to learn the objectives of humans accurately. So in this first section of the talk, I focus on how we learn from comparisons. Okay, so what is comparison data in robotics? First, the robot shows 2 trajectories to the user, and then we ask the user whether she prefers trajectory A or trajectory B. Her response gives us information about her underlying reward function. So let's go back to our Bayesian universal reinforcement learning from a few slides ago and add the comparison data into the framework. So in this new setup, we will have a second data set for comparisons, where each data point is a tuple that consists of 2 trajectories and a user response. So Xi A and Xi B are the 2 trajectories, and Q is the binary choice of the user between these 2 options. So how does this new data set affect our posterior? First, we are now given 2 data sets, demonstrations and comparisons. And we first factor out the likelihood of this new comparison data set. So we assume these 2 data sets are conditionally independent. And if I already know the reward function, then comparisons and demonstrations, as I said, they're conditionally independent. And similarly, we can expand the likelihood of the comparison data set such that each comparison is conditionally independent from each other too, like as long as the true reward function is given. And in the final step, we again make the noisily optimal assumption to model how humans give their responses to the comparison queries. But importantly, this assumption doesn't hurt us here, because it's not the humans who teleoperate the robot anymore. The robot is generating its own trajectories, and then the human user is just choosing which of them they prefer. So at the end, we have this unnormalized posterior, and by maximizing it with respect to W or taking its expectation, we get a good estimate of humans' reward function. And this is something we can easily do through like either sampling algorithms if we are going for expectation, or through some like optimizer software if we are trying to find the maximum likelihood estimate for W. And we implemented this and checked how well the robot achieves the task when it learns the objective using both demonstrations and comparisons. So here the data collected for two different algorithms have the same convergence rate in simulations. So in the Bayesian ARL one, we have several demonstrations, and for ours, we have only one demonstration and some comparison data. So as you can see, the Bayesian ARL robot, the one on the left, tries really hard to avoid the obstacle, but fails to achieve the actual task and gets stuck in a weird configuration. On the other hand, the robot trained with comparisons eventually reaches the goal while also not hitting the obstacle. So overall, the point is that the robot can learn from comparisons in addition to demonstrations. And in fact, they should, because we have this huge data problem in robotics. So we should make our robots learn from every possible source of information. And luckily, humans are better at comparing trajectories than giving demonstrations to the complex robots. And now that we talked about how robots learn the reward function of a human using comparisons, let's consider a more realistic setting where we are getting data from a group of people with potentially very different preferences. Or it can be the same person with non-stationary preferences. Let's discuss how we can learn an expressive model from this multimodal data. And when I say multimodal, I don't mean multiple data modalities. So we are still looking at comparative feedback, but the underlying data distribution is multimodal. Okay. Let's start with recapping the original problem we were solving with comparison feedback. We have a user who wants a robot to perform a task, and the user has an internal reward function that he wants the robot to optimize. But the robot doesn't know this reward function. For example, let's consider this scenario. Here we have the red autonomous car who wants to make an unprotected left turn. It's a difficult maneuver in autonomous driving. So it starts turning, but then it realizes the blue car, which is coming from the opposite direction and was previously occluded behind the red truck. So depending on its policy, the autonomous car may make different decisions now. If it's using a reward function it learned from a timid driver, the car may stop and give way to the blue car. So it could avoid an accident in this way. Okay, this is our first scenario. As the second scenario, we could think of a case where the data come from an aggressive driver, or maybe the same driver, but when he's in rush. In this case, the autonomous car could try to complete its turn before the blue car reaches the intersection. And this is just another way of avoiding the collision. In both of these cases, the autonomous car was using the data from one of the drivers, and either policy could work. They could both avoid the collision. And there have been many works that focus on learning such unimodal functions, including the learning from comparison technique that I just described. But what if the data come from multiple users or one user with varying preferences, and our robot doesn't know any of them? It doesn't even know who provided the data. So in the driving example, this would be a scenario where the autonomous car was trained using data from both drivers. So in such settings, we cannot really use standard learning from comparison techniques because the car would have an accident while trying to find a policy that's close enough to both drivers. And although there have been many works for the unimodal reward functions, learning multimodal rewards from comparisons was not studied. And let me explain why multimodal rewards are more difficult with an example. So here, this is the same robot as in the previous section, and now it wants to learn how and which shelf to place the banana. Perhaps a user comes in and says they prefer the first trajectory over the second one, and the robot can handle it because it knows how to learn unimodal rewards. But if a second user with different preferences shows up, then the robot will fail. In fact, it's doomed to fail. Let me explain why we cannot always learn multimodal rewards with pairwise comparisons by constructing a numerical counterexample. So we have two trajectories, xi1 and xi2, and this first user comes in. Let's say the reward for the first trajectory is 2 and then 1 for the second trajectory. But the exact numbers in the slide do not matter. I'm just using them for a consistent example. We again model the user's comparison response with the softmax model. So the probability that the user chooses a trajectory is proportional to the exponential of its reward. And this model will give us these probabilities. Now, we also have the second user with different rewards and preferences. And let's say the first user provides 20% of the data and the second user provides 80%. And combining these, our robot would observe a data set that is 24% in favor of the first trajectory and 76% the second trajectory. Now, the problem is, I can come up with another pair of users whose rewards and preferences are different, such that with different data frequency, they also provide the same data. So our robot is only observing these data at the end. Like from its perspective, these two settings are indistinguishable. It would have no way of identifying the underlying two rewards, like whether the green pair of users are the correct users or the blue pair is the correct users. And we can, of course, increase the number of pairs as much as we want. So there is some identifiability problem. And in fact, researchers in ranking theory, they proved that you can always construct such counterexamples where learning multimodal or even bimodal rewards from pairwise comparisons is impossible. So is there really no hope here? Well, no, because we can think of some generalizations of the problem. Specifically, instead of learning from pairwise comparisons, let's say we will learn from rankings of multiple trajectories. This helps because rankings are more expressive than pairwise comparisons. Like you might be thinking rankings are just many pairwise comparisons, but that's not the case here because first of all, we assume humans are noisy. So if we ask them to compare three trajectories in pairs, they may say A is better than B, B is better than C, but C is better than A. Like this wouldn't translate into a ranking. And secondly, our formulation dictates that responses are anonymous. This means if we make multiple comparison, like multiple pairwise comparison queries, we are not guaranteed to receive responses from the same user. And due to these two reasons, we cannot construct rankings from comparisons. And because rankings are more expressive, the robot will not suffer from the non-identifiability problem in the multimodal case. So in this work that I'm going to talk about, we are solving the problem of learning multimodal rewards using rankings. To reiterate, the robot is going to now show multiple trajectories to the users, and it will ask them to rank these trajectories from best to the worst. We will have multiple users, each with their own reward function. For example, they might have different preferences about where to grasp the banana, which shelf to put it, where in the shelf it should be placed, etc. And I will again use W for the parameters of the reward function, but here we will have multiple Ws, one for each user. And the ranking query will then be answered by one of the users with some unknown probability parameterized by alpha. And the robot will not know who responded to the query. The robot also doesn't know alpha, so it doesn't know the data distribution of whether some data come from the first user or the second user. Formally, we are given a set of trajectory rankings, and these rankings come from M humans who may or may not have different preferences. Or it can be just one human with varying preferences, but I'm calling them M humans just for consistency. And at the end, we want to learn the reward functions of these M humans. And for this, we will first model how humans respond to these ranking queries. In this example, let's say the first user is going to respond to this query, but our robot doesn't know this. So how does the human answer? It's really similar to what we had before. So we model the human as an agent who first noisily selects its best option. So we again have these probabilities that are proportional to the exponentials of the rewards. And the user's top choice will be a random sample from this distribution. Next, he will noisily choose his second best option. Now, the first option has already been selected, so we drop that. And the user's second top choice will be a random sample from this remaining distribution, of course, after normalization. And this process is going to continue, like it's going to repeat for the third best option. And eventually, there will be only one option left, which is the user's first option. This process, it's a very standard model for rankings done by humans. And eventually, what our robot observes is only this ranking. It doesn't know which user gave this ranking. It doesn't even know the probability that this ranking comes from this user. So it doesn't know the variable alpha. And now that we have a human response model, let's look at how the robot learns with it. From the robot's perspective, we have this user model. It doesn't know alpha, but it observed this ranking. And it will start with a prior over both alpha and user reward functions this time. So in addition to the reward functions, now I have this additional parameter alpha for data distribution. And it will then use Bayes' rule to update its posterior based on the ranking it observed. And this is very similar to, again, what we had with pairwise comparisons, except that we have this additional parameter alpha now, and of course, multiple different reward functions. And you can note that this likelihood term here is just the response model that I described. Like, given the reward functions and the data distribution parameter, what's the probability that I observe this ranking? And mathematically, we can expand it as follows. First, it's either the first user who responded or the second user. And we already know the first term here because alpha is given, and the first term here because it's just the same thing for the second user. And we can also expand the ranking probability conditioned on the user, because in that case, we know which user gave the response and we know their reward function. So this is just the ranking model that I described. And we can repeat that for the second user too. At the end, we have this full expression for the likelihood of this ranking query. And we know every term here for computing this likelihood value. Our robot will perform this posterior update for all the ranking data it has. And at the end, it will learn all reward functions. And in fact, it will even learn the data frequency parameter alpha. Let me show you some simulation results of this implementation. So on this robot task with bimodal data, we observed that modeling the reward as a unimodal function failed terribly. There were many outliers because the robot was trying to come up with one mode that explains all data. To get nicer graphs, we had to also plot the median error. On the other hand, modeling the reward as a multimodal function using our mixture model gave much better performance and learning, both in terms of mean and the median. And the results were similar on OpenAI's Learnir, where we again simulated the bimodal reward. So here we demonstrated rankings can be used to learn multimodal reward functions, and one can also think of other forms of comparative feedback. But overall, the point is that these richer forms enable us to learn more general, more expressive reward functions. And it's great that we can learn from these various data sets like comparisons and rankings, but even if we were to use these more reliable and expressive sources of information, we still haven't solved the data problem. Like, we simply do not have large data sets, let it be demonstrations or comparisons, when it comes to robotics applications. So instead of blindly collecting large data sets, we should have more intelligent approach that optimize what data we should be collecting. For example, we should try to find the most useful comparison queries. So I will now talk about how we can intelligently elicit user preferences in a way that improves data efficiency. And for this, we will develop active learning techniques. And of course, active learning has been studied both theoretically and practically. Like, if you are working on machine learning, perhaps you might have seen plots like this, where in orange, we see the convergence results of active learning, and in blue, it's just random sampling. And the point is they're really close. So you might be thinking that active learning doesn't give practical benefits in many domains, like random querying or random data generation is often good enough. But that's not the case in robotics, because as we just saw, it's very difficult to collect data in robotics. So we are particularly in the very low data regime and would like to collect as few samples as possible. And also, active learning can help elicit more reliable human feedback. So it has attracted a lot of attention in robotics. For example, there was a work that came out of OpenAI and DeepMind in 2017, where they were able to teach some unusual behavior to these simulated robots using a few thousands of human comparisons. More recently, researchers at Berkeley, and this is actually Peter Abiel's group, which we have been talking about before the talk. So these researchers proposed a reinforcement learning algorithm that makes use of pairwise comparisons. And you might notice that we have been talking about a similar problem here, similar in the sense that we are trying to learn something using comparative feedback. But again, there's an important difference when we are working with real robots. That is, we cannot really make thousands of queries like what is done in these works in simulation. That would take too much time. And besides, a human needs to watch these trajectories and compare them or rank them. And that's a very costly process. So in this last section, I will show how we can actively query the users for comparisons so that we can work with real robots. And the same ideas apply to rankings or other forms of comparative feedback too. One thing is very important to note in our learning problem. So in the case of demonstrations, we have a user giving demonstrations to the robot. We had control over nothing. It's the user who decides the entire trajectory. On the other hand, in comparisons, we again have the robot and the user, but now the robot first shows some trajectories to the user, and then the user responds. We again have no control over the user's response, but we do have control over what trajectories to show. So we can actually find an intelligent way of choosing these trajectories to, for example, accelerate the learning of the objective. One way of actively generating these comparison queries is through a method called maximum volume removal. What this method does is to start with a posterior distribution given some demonstrations and comparison data. And now let's say we want to query the user once more for a new comparison data sample. And we want to do this in an intelligent way to improve data efficiency. So we will optimize the trajectories in our query format. So in this maximum volume removal method, we first take some samples from this posterior, and only for visualization, let's say our feature space is only two-dimensional. And these are, let's say, the samples from this posterior. So these are basically our hypothesis for the reward function. Let's say we now want to assess how good, how informative this query is. So each of these parameter vector samples will tell us how likely the human is to choose the first or the second trajectory. So here the green bars correspond to the trajectory on the left and the orange ones to the trajectory on the right. If the human chooses the trajectory on the right, then the samples which give more weight to the other trajectory are less likely to be the true hypothesis. So we will update our posterior and we may not sample those vectors again, because we almost already know the user's because we almost already know that the user's choice is not explained by those vectors. But looking at this query, it's not really very informative, because in this case, just by looking at what our W samples predict, we almost already know the user is going to choose the second trajectory. It's very unlikely that they are going to choose the first trajectory. So in expectation, we will not be able to remove a lot of volume from our hypothesis space. Let's instead look at this other query. And for this one, our model is more uncertain. Like regardless of which trajectory the human is going to choose, we will be able to remove some good amount of volume from the hypothesis space. So it makes sense to make this query rather than the previous one. So what maximum volume removal objective is trying to do is to evenly distribute the probabilities on the two trajectories. And we implemented this, this volume removal based active querying approach on a number of simulation environments, and it indeed improved the data efficiency. So here y-axis shows how well the learned objectives align with the true objectives. So higher is better. And these are on some benchmark environments that include the driving simulator and environments from OpenAI Gym and Mojoko. So it worked great, but it turns out there's a problem with volume removal. Let me show you what it is. So volume removal decided that the query on the right gives us a good amount of information based on maximizing the volume that would be removed from the hypothesis space of W's. And it would be even better if it were like this, because the volume would be evenly distributed to two trajectories. But let me show you another query. This is a query where we are showing two identical trajectories to the user. Like obviously, this will not give any information about the reward function because the user's choice will not reveal anything. The robot is just repeating the same trajectory and asking which one is better. But all samples will, of course, predict equal probability of choice for the trajectories because they are just the same trajectory. So from the volume removal objectives perspective, this query is a great one. It evenly distributes the probability, right? And in fact, this is one of the many globally optimal solutions. Volume removal objective, in fact, has many globally optimal solutions, but some of them are just terrible. They don't give any information. And the reason for this is the volume removal objective tries to maximize the model uncertainty, but it doesn't take the user uncertainty into account. As long as the model, the robot, is uncertain about the outcome, the volume removal objective is maximized. So this approach, it intuitively made some sense, and it was the state of the art. But we realized it works in practice only thanks to the local optima of the optimization. So to solve this problem, we formulated the active querying problem with an information theoretic objective, which not only considers the robot's uncertainty, but also models the human uncertainty in responding to queries. So here we maximize the mutual information between the user's response and the belief about the reward function, conditioned on the data sets and the query that we are going to make. Like equivalently, we can write this objective as the difference between two entropy terms. Here, the first term quantifies the robot uncertainty because it's conditioned only on the previous data, and we are still trying to maximize this. The second term, on the other hand, is conditioned on the true reward parameters W, so it quantifies the user's uncertainty. We are trying to minimize this so that the user responses will be reliable and we can gain some information from them. So going back to our example queries, the model uncertainty is maximum for both of them because in both of them the robot doesn't know which trajectory the user is going to choose. It's like 50-50. However, for the first query, the user uncertainty is also maximum because regardless of the parameter sample, the user will also have 50% probability of choosing each option. But the query on the right minimizes the user uncertainty because the user will be very certain about their choice given a parameter vector sample W. And in the end, we also implemented this information gain-based approach, and it significantly outperformed the volume removal methods. And in our simulations, we were able to learn users' objectives within as few as 30 queries, as opposed to 100 in the previous results. We also conducted user studies in the same robot environment as before. And as you see here, the volume removal objective queries very similar trajectories, whereas the mutual information-based method generates a more distinguishable query because it takes the user uncertainty into account. So we have seen how active preference-based learning can help us better learn models of human behaviors, rewards, or policies. And besides the works I've mentioned so far, I've been working on a number of other directions in the space of active learning, which unfortunately I don't have time to talk about in detail today, but of course I'm happy to discuss any of these directions offline. Let me briefly mention three core categories that I've been working on. So first, I developed richer forms of comparative feedback, such as scale feedback using a slider, which enables users to indicate how much they prefer one trajectory over the other. And these richer forms enabled us to learn more general reward functions in a data-efficient way. I also looked at how we can use the comparative data, such as latency and price trade-off in Uber and Lyft, to reduce traffic congestion through pricing. And finally, I developed active preference-based Gaussian process regression techniques that go beyond simplistic reward assumptions, such as linearity, and apply them to exoskeleton gait optimization. So here, the patients cannot possibly give demonstrations, and testing is very demanding for them, so data is really, really expensive. And the active learning approach that we develop use comparisons, and they enabled us to quickly learn the patient's preferences. And these active learning ideas using information gain has also applications outside robotics too. For example, in my internship at Google, I worked on preference-based learning and recommender systems, and we looked at movie recommendations where users can just watch a movie, or they can give us feedback about whether they want more or less of an attribute, such as funniness in this case. And at Google, they previously considered expected value of information another metric for optimizing queries. But if you maximize the mutual information instead, then we get higher success and lower failure rates, as it enables us to find the best movie as quickly as possible. The recommendation systems are slightly different though, because we should make sure we are not making bad recommendations just for the sake of learning. So I developed another variant of the approach, which we call myopic information gathering, and the results got even better. So overall, the key takeaway is that comparative feedback can be actively collected, and we can use different acquisition functions depending on our objective. If we are trying to learn as quickly as possible, then the robot should ask questions that it doesn't know the answer, but the human user does. So I talked about how comparison data can be helpful to learn unimodal reward functions, and using rankings enables us to learn multimodal rewards. I also talked about how we can make robots actively collect such data. More recently, I started working on how robots can use learned human behaviors to better interact with them. For example, how can they collaborate if they're able to predict the actions of humans? Or how can they tap into large offline data sets, including multimodal data, to learn more expressive and generalizable policies? Finally, if robots can predict our actions, this means they can realize our weaknesses. So we can use such robots to teach us or improve our skills. Overall, I'm convinced that we need such algorithms that can model other agents for multi-agent systems. And one efficient way to do this is to learn their objectives. And I believe this is not only good for partner modeling, but it can enable us to get various other benefits, which can improve the capabilities of both the robots and ourselves. With that, I'd like to end by saying thank you to the faculty and research scientists and all the amazing people I've had a chance to mentor or collaborate with. And of course, these works have been possible thanks to the funding by several agencies and companies. And because this is PhD application season, I have an extra slide. This is my VR hiring slide. Next year, I'll be starting at University of Southern California as an assistant professor, and I'll be hiring PhD students. I believe there are still 3 days left until the application deadline. So if you are interested in applying to the PhD program in the US and especially in USC, maybe shoot me an email and we can talk in these 3 days. And with that, I can take any questions.